Here it is, our final analytical technique, which we will be learning about by taking pieces from chapters 21 and 22, and that's all we have time for in the rest of this class. So this technique is called chromatography. And for the next few videos, we're just going to go over fundamental ideas behind this technique before we get into actual analytical uses. So first I'm going to show you a visual of chromatography in action and define some terms, and then we're going to write down the key points and try our best to mimic this visual with drawings. Now let me give you a primer for what you're about to see. In chromatography, we dissolve a solute mixture and separate the solutes from each other by passing the mixture through a column that retains some solutes longer than others. In other words, if we have two chemicals represented by this green band of chemicals here and this red band that's hard to see right now, but there is a red group of chemicals behind that green, what we're going to do is we're going to pass them through this column, and one of those chemicals is going to go slower through the column than others. In other words, it's going to be held up by the column or retained in it longer than the other one, and that's going to allow them to separate from each other. Why we would care about separating them? Well, that's for later. Right now, we're just learning fundamentals, not the analysis part. But the point is, this column is going to be used to separate these two chemicals from one another. And we call that starting mixture the eluent. It's the fluid that's inserted at the beginning of the column that contains the solutes of interest. And then we're going to start flowing them through the column in a process known as elution. And as the chemicals separate, they'll exit the column at different times. And the whole time we're keeping track of how much time has passed. And time is what's actually plotted on the x-axis of our data. We just keep track of how much time has passed and when chemicals start being detected. So let's see this in action. Right now, the red and green chemicals are mixed together. They're at the same starting point, but then we start the flow. And we can see that the green is separating out from the red. It's traveling faster through the column. It makes it out, and we measure it. Then later, the red makes it out, and we measure that. One thing to notice is that while the two chemicals were separating from each other, they were also starting to spread out more than when we first started, and they were contained in a much more narrow space. Let's see that again. Right now, everything's compact. Green starts to move faster than red, but we can see green is spreading out more and more, as are the red chemicals. And now red comes out, and finally red stops coming out. And so notice these peaks were created at the exact same time that the bands, as we call them, started coming out. And the maximum value of the peak, that was detected at the same time that the center of the band made it through the column, because this is where the bulk of the chemical solute particles remain, is in the center. But we see that some of them just get a little bit ahead, and some of them lag behind. We'll get into why that happens and why it's important in a future video. Just keep it in mind for now. So let's try to write all of this out as best we can. Chromatography. In this technique, we dissolve solutes and separate them by passing the mixture through a column. Dissolve solutes and separate by passing the mixture through a column. By passing mixture through a column that retains some solutes longer than others. That retains some solutes longer than others. In the previous visual slide, we saw that the red chemicals were slower than the green because they were being retained by the column longer. Now let's just draw a couple of snapshots of the chromatography process. So let's draw a crude column represented by this rectangle. And at the very top, we're going to draw two chemicals. Rather than color code our different chemicals, we will use different symbols. So we'll use a thick black band to represent solute A. Then we'll draw a band of just slashed lines, which will represent solute B. So we have bands of A and B solutes. The solutes are contained in some solvent. And we call this solvent the mobile phase. Because beyond just containing those solutes, we're going to flow this solvent through the column, and it's going to pull these solutes with it. However, as we saw in the animation, some solutes will travel faster through the column than others. Why is that? Well, because the column is going to be packed with particles that interact with those solutes and slow them down as they try to leave the column. And again, some solutes will interact with these particles more than others and thus be retained by the column or slowed down more than other solutes. And that's how we get our separation. So we call these particles column packed with particles. We call these particles the stationary phase. Because they don't move. They're just sitting in that particle interacting with the solutes, whereas that solvent is actually being flowed through the column and is trying to get those solutes out. Hence, again, we call it the mobile phase. To give a bit more details on both of these phases, we will say that the mobile phase flows through the column and carries solutes with it. Flows through column and carries solutes, or just sols for short, with it. The stationary phase, on the other hand, is a substance that stays fixed in the column. Substance stays fixed in column and interacts with solutes. And interacts with sols. In other words, slows them down. So this picture here represents the start of the experiment. Everything's mixed together at the very beginning of the column. Nothing has started flowing. So we could say start, or we could be specific and say time equals 0. Nothing has begun yet. Now I'm going to erase some of this information and draw a column that represents the middle of this process. Let's quickly redraw another column. Packet full of particles. But we'll label that this column represents later. And at this point, the two solutes have separated from each other and the bands of solutes have spread out. So let's say A is retained by the column longer than B. And A is what we are representing as just a dark band. So this is solute A. Meanwhile, the B chemicals, which we represented as these dashes or slashes, they've made it further along. Notice I'm drawing the bands wider than when we started. Again, these things do spread out from each other over time as well. We'll get into why later. For now, let's focus on the process that's occurring. This process is known as elution. The process of a gas or liquid flowing through a column. Process of gas or liquid flowing through column. Right now we're talking about liquids. Liquid solvents pulling dissolved solutes through a column. But later in this unit we'll get into gas chromatography, as it's called. But for now, let's keep our focus on liquids. A thing to note, solute A interacts more with the particles in the column. Solute A interacts more with the particles in the column, the stationary phase. Particles in the column, stationary phase. That's why it's further behind in the column. For reasons we won't concern ourselves with right now, these chemicals interact with the particles more than these chemicals, and thus they are slowed down by the column more than B, and that's what allows this chemical to get ahead and separate from these chemicals here. Chromatography is ultimately a separation technique, which we'll see later in this unit makes it a very powerful technique for analytical chemistry. But right now we're sticking with fundamentals.